Okay, hello again. This is the second video on chapter 5. So let us continue. I hope you're doing well. So this is what we want to do. So we want to talk about the definite integral. What is definite integral? Okay, that's what we want to do. We talked about the idea of finding areas under curves, right? So if you have a function, we want to find the area under it, and that idea cannot be done by using geometry. To find this irregular shape, the area of it, you're going to have to use calculus. So we learned about the method of exhaustion. So now we want to define it. So the notation for it is the summation notation, and we talked about that as antiderivative, remember, in end of chapter 4. So now we want to define it using this idea of limit. So if you want to find the area under a function, what we are going to do is we want to take the area under the function, divide it into, let's say, from here to here, from A to B. We divide it into partitions, n partitions, right? And then we are going to either use left end or right end point to find the height of the rectangles here, the heights of the rectangles, right? So what heights they're going to have depends on what number we pick from each partition to find the height. So if you pick the left one, then the height of this rectangle would be this much. If you pick the right one, the height of this rectangle would be that much, right? So that x star is actually the number that we pick from each subintervals, right? So the numbers that we pick from these subintervals, those are x sub star, and then we have n subintervals here, and so x1 star would be the number that we pick from the first subinterval right here, and so forth. All right, and then delta x, of course, is the partition, the length of the partition. And the formula for delta x, we talked about that already, is b minus a divided by n, right? And then, so what does this sigma give us? The sigma gives us the sum of the areas of these rectangles. And what does the limit do to it? Well, the limit would be the area under the curve when n approaches, the limit of this sum when n approaches infinity will be the area that we're looking for, which is the area under this curve, right? From this curve to the x-axis, from A to B. So that is given by this notation here, which we read as definite integral of f of x from A to B, definite integral of f of x dx from A to B. And that's the definition of it. So we are going to find areas under functions using this definition. It's not always easy to do that. In fact, it turns out to be much harder to find these areas than what we did with the slope of the tangent line. So this limit is not easy to find, but we're going to look at some easy ones to learn what this limit is all about, and then we continue with this integration and finding areas under different curves in calculus 2. All right, so if this limit exists, then what do we say? We say that this function is integrable. Integrable means you can integrate it, actually. So is integrable in this interval from A to B, or is an integrable function. Okay, So let's see how we're going to do this. So this gives the area under f of x from a to b, right? Now notice that we're not assuming that f of x is a positive function. So in this case, f of x could be above the x-axis or below. And we're going to talk about what it does to this sum in a moment, okay? All right, so note that like the index in a sum, the variable here is a dummy variable, so it doesn't matter what letter you put here, the answer doesn't change, right? So it could be f of x dx, it could be f of t dt, or f of u du, doesn't matter. So this is a dummy variable, and it could be changed to any letter. All right, so it says use the definition of the definite integral to evaluate the integral. Use a right endpoint approximation to generate the Riemann sum. Remember, the Riemann sum is this right here, right? So in order to do this, we have to actually build this, right? Now, to build this Riemann sum, we need f of x of I, and we need delta x, right? And we need to decide what number in subinterval we're going to pick from. How do we want to pick a number in a subinterval? And that is left or right. Here we are told to use the right endpoint, right? So we're going to use that formula. All right, so this is our goal here, to find this sigma, the structure of it. Once we find it, we need to take the limit of it when n approaches infinity, right? So let's do this. So the first thing we need to do is get our interval here, which is from 0 to 2, right? So the interval from 0 to 2, we have to divide it into n partition, right? How do we divide it into n partition? That's easy. Delta x is b minus a over n. So it's 2 minus 0 over n. So it's 2 over n. So we got that. So that's our delta x right there. Now to find f of x of I, first we have to find x of I. Now when we do this, when we do this, 0 to 2, and then we divide it into n parts, well, how do we find that one? We talked about that in the previous video, but to find that one, we have to take this number and add delta x to it. To find the next one, we have to add 2 delta x's to 0, to the first number. In this case is 0, it could be a, right? It could be any number. And to find the next one, again, add another delta x. So it looks like the formula for x of I is what? Is x of 0 plus I times delta x, right? And what is x of 0 here? X of 0 is the first number, which is 0. So it's 0 plus I times 2 over n, because delta x is 2 over n. So our x of I turns out to be what? That. Now, this is not what we want. We want f of it. So we have to take this and substitute it for x here, right? So f of x of I is going to be x of I to the second power, and x of I is 2i over n. So this is what we need. So that goes right there, right? And delta x, of course, goes there, right? So we have our sigma. So let's build it. Here we go. So here's a sigma, right? So we got, remember, it was f of x of I was 4i squared over n squared. Our delta x was 2 over n, right? So here we go, we put them there. That's delta x, and that's f of x of I, right? Now, we simplify it a little bit. So there's a 2 here, right? Multiplied by 4 is 8, and I squared. There's n squared here, and times n is n to the third power. So now we can take this stuff that don't have I in them out of the sigma notation, because sigma notation only applies, this formula is the formula that has I in it. So we keep the I squared inside. We take the rest of it out of the sigma, right? Okay, now this is what we have to take the limit of, right? Now, obviously, we're not going to be able to do that because I is not n, and we want n to go to infinity, so we need to get rid of this I. How do we get rid of it? In fact, we have to get rid of this whole thing. We have to get rid of the sigma, right? How do we get rid of the sigma? Well, that's why we learned those formulas, remember? We had sigma a constant, sigma I squared, sigma I to the third power, right? The formulas that we learned previously. So let's do that. So we know the formula for sigma I squared is this right here. So we replace I squared by this formula, and n is n, right? Remember? So now we have an expression we have to take the limit of when n goes to infinity. But in order to do that, let's simplify it first, right? So we're going to do this multiplications and then simplify it. This is just algebra yet. We multiply, we simplify. This is a common denominator, so we can give it the same denominator, and it simplifies into this. You can stop the video and make sure you get the algebra here, how we got from here to here. But this is the expression we have to take the limit of, right? So let's take this and take the limit of it when n goes to infinity. So here we go, this is what we got. So when n goes to infinity, this goes to 0, and this goes to 0, right? And if that goes to 0, that goes to 0, because n goes to infinity, then the only thing left of this would be 8 over 3, right? So the answer is 8 over 3. And that is, believe it or not, exact answer. That means if you draw x squared here, right? Of course, we don't need the other part of it, but we know it looks like this, right? Now, if you go to 2, about right there, the area under this curve, right here, that area, even though there is no geometric formula to find that area, we know exactly what that area equals to. That's just an amazing thing about calculus, because we can't really use any geometric formula to find the area, but using calculus we got an exact answer. Now remember, we could, of course, we didn't want to do that. We knew we didn't need calculus to do this, right? So if you wanted, you could divide it into grids, like rectangles or grids or whatever, and approximate it and get as close as you want to the real answer, but you will never get the real answer this way. So you have to use this idea of either limit or infinitesimal, right? So you assume that the rectangles are so many of them, that the width of each becomes so small, right, that we can ignore the error. That's the idea. Of course, we use limit. All right, now we don't really do this to find this. We're going to learn, it's very easy, in fact. We're going to find, it's called the fundamental theorem of calculus. In the next section, we learn that. To find 8 over 3, all we have to do is find the antiderivative of x squared, which is x to the third over 3. And then we're going to evaluate that from 0 to 2. So that means we put 2 for x, which is 2 to the third over 3, minus, and we put 0 for x, 0 to the third over 3, so we get what? 8 over 3. It's very easy to do that, but the point is to learn where these structures come from and in order to learn more mathematics, you need these concepts and structures in your head. Okay? So let's move on. It says express the limits as integrals. Well, here's a limit of some function. Somebody actually created what? Created a f of xi and delta x for us, right? And looks like really easy. First of all, we know integral goes from 0 to 2, right? Because we're given here. And then what goes here is f of x, but our f of x looks like is 5 times something squared minus 3 times something to the third power. Well, obviously, the f of x is what? Is that. So that's out of f of x, and that's dx. Delta x becomes dx when we do the definite integral, right? Okay, here's another one. What is that? Well, look, there is delta x, and we go from 0 to 1 again, from 0 to 1. And our f of x looks like cosine of something squared, right? Cosine of what squared? Well, 2 pi x, right? So the answer is cosine squared, cosine 2 pi x squared, right? dx. And then the limit is 0 to 1. All right, let's do one more. Now in this case, we are given a left-hand sum, and it says given this left-hand sum, express their limits as n goes to infinity as definite integral, right? So we want to express that as a definite integral, identifying the correct intervals. Okay, to do that, we know this structure looks like what? This structure is actually, this is f of x of I, right? X of I minus 1, oops. Why? Because it's a left, right? It says left here. So it's f of x of I minus 1 times delta x. That's what we put here, right? So this right here is actually f of x sub I minus 1. And this right here is our delta x right there. Okay? So let's see. So we say this has to be actually f of x sub I minus 1 delta x equals to that. So this part is f of x sub this should be I minus 1. I'm going to fix it, but this is I minus 1. And this is what? Delta x. So what is x of I? Well, we know if you divide the interval from a to b into n parts, right? Then each part would be b minus a over n, right? And that's our delta x. And then to get each of these, we know what we have to do. We have to take the first number and add delta x to it. To get the next one, again, add another delta x. So x of I is a, which is the first number, plus I times delta x. So I want this one, which is like, let's say, you know, whatever number that is. That number is the same as I, so x sub 5 would be a plus 5 delta x's. Okay, so now I don't want that because this is the left end point, and the formula, remember from the previous section, formula for left end point is this. Formula for right, we write f of x sub I, right? Okay, so to find x of I minus 1, we just substitute I minus 1 for I, right? And we get this. And what is our, so what is this? Well, that's our x of I minus 1. Now, what should delta x be? Delta x is b minus a over n. Remember, we don't know what b and a are, right? Because we are not given them. So delta x is b minus a over n, right? And we are going to find in a second why a equals to 0. But for now, b minus a over n has to be 1 over n. So from here, we can get for sure that b minus a has to be 1. We don't know what b and a are, but we know the difference has to be 1 because that's what we are given, right? This is delta x. Okay, now, how do we know a is 0? Well, we're going to see that. We know x sub I minus 1 equals to this, right? Because delta x is what? 1 over n, so we're going to put it there. So f of x sub I minus 1 has to be f of whatever this is, right? So we put it there. You just put I minus 1 in the numerator here. Now this, remember, this is f of x sub I minus 1. So it has to equal to what we are given here. So notice right here, f of something equals to I minus 1 over n. Well, that function has to be actually x because it looks like itself, except has an extra a. Well, the a has to be 0 then for this to equal to this, right? The function has to be x and a has to be 0. All right, if a is 0, right? If a is 0, we know b minus a has to be 1, so b has to be 1, right? That's how we know the answer. A is 0 and b is 1 and the function is x, okay? So that actually is our answer right there. Again, stop the video and see, make sure you understood what I just described here. That's the answer for that. Let's do one more of these. Here's another one. Again, we are given a structure here that we know that, again, this is our delta x, and this whole thing is f of what? Is f of x of I. In this case, is f of x of y. Why? Because is the right endpoint, right? So this for right endpoint, the formula is f of x of I times delta x. And in this case, this is our f of x of I, and this is our delta x. Again, just like before, we know x of I has to be a plus I delta x. Here, we don't convert it to x of I minus 1 because we do need x of I. So this is x of I. We know delta x is 1 over n, so that's our x of I. And delta x is 1 over n. So b minus a has to be 1 here, we know, right? B minus a has to be 1 because delta x is 1 over n, so 1 has to be b minus a. We don't know what b and a are, but we know b minus a is 1. Okay, now, this structure is given by f of x of I, all of that, times delta x, right? So again, we know x of I is that. So f of x of I has to equal to this whole thing. And notice that in order for this f of something to be this, that something is like x, think of this as x, right? So it looks like it's x times log of x squared, right? So that means here we know that our f of x is actually this right here. And what about our b? Well, here notice that it looks like a has to be 1, right? Because this looks like a plus I over n, so this is 1 plus I over n, right? So that means what? That means our a has to be 1. And remember, if a is 1, then b has to be 2, right? And that's how we find a and b, and that's how we find f of x, and that's how we get the answer. Okay, so this is just practice with that structure. So we're going to work a little bit more on this later, but for now, that's just the practice to understand that structure of the sigma that we used here. All right, now, as I said, here we assume that the function can be positive or negative, right? What happens if this function is actually negative, if graph goes below the x-axis? Well, then, when you find your you find x star here in this interval, then the height of it will be a negative number, right? If the height of it is negative number, right, whatever in this case looks like this is our x sub Let me clean that mess. So in this case, looks like this is our x star. This is our x star sub whatever this number is, right? So the height is actually negative. So f of it would be a negative number. And remember, delta x here is positive, so positive times negative would be negative. That means inside here, which we have f of x star, right? Maybe I or I minus 1 times delta x. These would be negative values. And when you add a bunch of negative values, right, over here, you get a negative value. But over here, you get a positive value. So that means the total area, if you think of net area, when you add these rectangles, looks like we're going to have negative area and positive area. And it's possible that the answer to our sum of the rectangles would be 0, negative, or positive, right? So the quantity A1 minus A2 is called the net signed area. Now, what do we mean by A1 minus A2? We mean the positive area and the negative area. When you add them together, you get net area, and that's the net signed area. So in calculus, we have such a thing as signed area. All right, so here is an example. Evaluate the integrals of the function graph using the formulas for the areas of triangles and circles. Now, here we are not going to be able to use the definite integral for these functions because we don't know how to integrate these, right? So do we know how to integrate something like that from what? From 0 to 2, things like that. We're not going to be able to do that. So what we have to do, we have to rely on what? We have to rely on geometry. So let's use geometry. What's the area of a circle? Well, pi r squared, right? So pi r squared. But what is the radius of this? It looks like the radius is 1. So it would be pi times 1 squared, which is pi. But that would be the area of the complete circle. We need half of it, so we have to divide it by 2. So that would be the area of that part, which is of course positive because it's above the x-axis. What about this one? Well, that's a triangle. What's the base? 1, 2, 3, 4. What's the height? 2. 4 times 2 is 8 divided by 2 is 4. And since this is below, this is negative. Right? This is positive, this is negative. So that would be negative 4. Again, for the same reason, the area of this would be half of the complete circle. And notice that the radius here is 6 divided by 2 is 3. So 3 squared times pi, that's 9 pi, and I have to divide it by 2 because it's half of the circle. So that one is that, and it's positive. And if you add all of these, you get 5 pi minus 4. Okay? All right. So signed area versus total area. So if you leave the definite integral this way from A to B, then what you get here is actually net area. What does that mean? It means that if the function goes up and down below and above the x-axis, let's say you find the area from here to here, right? Now this would be positive, this would be negative, this would be positive. So the answer would be whatever the total is here. Now it could be more than one area. Here there are just only 2 of them, but it could be more. But the answer is the net area, right? But the total area, what if you want to find what is the sum of that plus that plus that? You want to add the positive areas. In order to do that, you have to take the absolute value of f of x. And you know, absolute value of a function makes it positive. So if this is f of x here, when you take the absolute value, this part of it comes up actually. So it becomes like that. and when you find the definite integral of f of x with the absolute value, you are going to end up with a positive answer. Okay, so this would be the total area, and this is net signed area. All right, so let's talk about properties of definite integral. Definite integral of a to a equals to 0. Think of a function. Let's say this is the function. You want to find the area from a to a. Well, from a to a, there is no area here, because from a to a, there is 0 distance. So this is obviously 0, right? So if the two, the lower and the upper limits of the definite integral are the same, then the answer is 0. Okay, now what if you switch the order? Let's say this is a to b. So integral from a to b, right, of f of x dx. Well, from a to b, we know the delta x would be what? Delta x is b minus a over n, and is positive, right? Well, how do we know this is positive? It's because b here, I have to put b here, b is bigger than a. If b is bigger than a, b minus a is positive, and we know n is positive, and positive over positive is positive. So the answer, b minus delta x, is positive. But if you switch them and put the b here and put the a there, what happens with delta x? Delta x becomes negative, because again, b is bigger than a. So if you do integral of 3, you put 3 there and you put 2 there, that would be negative of integral from 2 to 3. Okay? So integral from 3 to 2 is negative of integral of 2 to 3. That's the idea. Okay? So that's the second one. The third one says the integral of a sum, definite integral of a sum, is the sum of definite integrals. Definite integral of a difference is the difference of definite integrals. If you have a constant multiplied by the function inside here, integrand, then we can bring it out and put it outside. So for example, if you have 3x squared dx from, let's say, 2 to 5, we can write this as 3 times integral of x squared dx from 2 to 5. You can put the 3 out. And the last one has to do with this idea. If I have a function, I want to find the area from a to b, and c is some number in the middle, then we can say that area of f of x from a to b, that means this whole area, right, is equal to the area from a to c, right, which is this area here, right, plus the area from c to b, right? And that actually works. Okay, so these are properties of definite integrals. Let's look at an example. It says compute the integrals given that the definite integral from 0 to 4 of some function is 5, from 0 to 2 is negative 3 of f of x. And for g of x, from 0 to 4 is negative 1, and from 0 to 2 is 2. Now what we have to find is this right here. How do we do that? Well, what is this? This is the sum. This is the definite integral of a sum. So it would be sum of definite integrals, right? So we turn it into a sum. Now we are given this, and we are given this. Where is it? Right there. So it would be 5 plus negative 1, which is 4. What about this one? Well, this is the, again, definite integral of a difference. And these numbers can go outside, right? So we can write it as 4 times definite integral of f of x from 2 to 4, and then minus 3 times definite integral of g of x from 2 to 4. Now we are given this. That one we are given is so what we're going to do is, did I give you that? Looks like I haven't. Well, but remember something. Remember that note. From 0 to 4 is the same as from 0 to 2 plus from 2 to 4, right? And if you want to find from 2 to 4, you can take this and subtract it from left side, right? So since we are given from 0 to 4, which is right there, and we are given from 0 to 2, which is right there, we can subtract them and find this one from 2 to 4, right? So that's how we get this. And so it would be 4 times whatever it is minus 3 times whatever this is. And we know that is 4 times whatever that is. What is that? Well, 5 minus negative 3 is 8, right? So that's 8. So 4 times 8 minus 3 times 3, right? Again, this is G is not given from 2 to 4, but we can subtract them. So it would be 2, right? We got 2 minus negative 1, which is 3. Which is, so it would be negative 1 minus 2, which is negative 3. And negative 3 times the negative 3 would be positive 9. And that's 41. Okay, let's just see right here. All right, so let's see. Now, the average value of a function is an interesting idea. Let me talk about it here, and then we look at the formula. So if you have a function, let's say we have a function, here we go. Now we want to find the average value of a function from A to B. Now believe it or not, this is a tricky question, because you see, if somebody says, what's the average of 1, 2, and 3? Well, we just add them and divide by 3. What do we get? That's what? That's 6 over 3 is 2, right? But what if somebody says, what's the average of all of these function values? How many function values do we have from A to B? Well, infinite, you know, there are infinite function values. For every x value, there is a y value, right? So how do we add infinite number of function values and divide them by infinity, right? So we have to add all of these, f of x1, f of x, 2, f of, all the way to, infinity, and then divide by infinity. That's impossible. So what do? We're going to use a calculus trick. So here's the calculus. What we're going to do, we're going to take, let me explain one more thing, then we look at it. So if this is a function, we're going to take the distance from A to B and divide it into, again, n parts. And we're going to take each of these x values, right? Each of these x values. So we're going to start from x of, x of, 0 plus f of x of 1 plus ... all the way to f of x of n, right? Like that. And divided by what? Divided by n. That's what we're going to do. So we're going to pick n numbers. So you start with 1, and then go to 2, and then go all the way to n. And then increase n, right, number of numbers that we're going to pick, then take the limit. See? So we can use that trick of the idea of limit here. So we're going to start with 1, right? Pick the first one, and then all the way to n, right? And then these are just the ones that we pick, right? Again, you divide the interval into, we still have bunch of subintervals all the way to what? To n. And then we're going to pick numbers here from each interval. And those numbers are our x stars, right? From first interval, we pick that one. From the second interval, we pick that one, and so forth. Okay, now what happens? Well, look, we are going to have a sum here, and then divided by n. But we know delta x is b minus a over n, so n is b minus a over x, right? You know, you could just switch these two. So this is our n, so why don't we just put this where it belongs here, right? So we get this formula. And then if you just put the delta x over here, right? Just multiply by reciprocal of this. What's the reciprocal of this? Is delta x over b minus a, right? So delta x goes in the top and b minus a goes down. Now notice that when we take the limit of this, when n goes to infinity, this part should be familiar to you. What is this? That's actually famous what? Famous Riemann sum. So this is actually the integral, the definite integral of f of x from a to b, and the denominator is just b minus a. So it looks like we have a formula to find the average value of a function in an interval. That's an amazing formula because it can, this way you can actually find the average of infinite number of numbers. You can sometimes in textbooks they write it this way and we write f average. So f average from a to b is given by this formula or this one. Okay, now again we're going to talk more about this in calculus 2, but for now let's do an example. Now remember we calculated this integral previously, so I'm just going to use the value of it, which is 8 over 3, right? So what's the average of x squared? So if this is a function x squared, we want to know what's the average from 0 to 2. Now obviously there are infinite number of function values here, right? If you take all of those and add them and divide by infinity, what do you get? Well, we're going to find out what we get. We are going to get what? Using this formula, we're going to get 1 over b minus a, 2 minus 0, times the definite integral from 0 to 2 of x squared dx. So it's 1/2, and we know again, previously, the value of this is 8 over 3. So the answer is 4 over 3. Okay? That's the idea of average value of a function in an interval. Okay? So I'm going to stop the video here, and then in the next section we're going to talk about fundamental theorem of calculus. Okay? So I'm going to say bye to you. I see you in the next video. Take care of yourself and others. Okay?